All right, guys, let's get started. Sorry, looks like we are half an hour delay into the session, but that's fine. We'll try to make up whatever we have lost in this. So, welcome everyone to the session on Apache Spark, hosted by Tech Canvas, and going through some of the primitive concepts of Apache Spark in this session, and also I'll be going through some of the examples towards the end of the session, if you have enough of time, and then we'll take some questions from you. All right, let's get started and let's see what we've got for you today in this webinar. This webinar, we'll start off with understanding some of the basics, MapReduce paradigms, and we'll see how and what kind of challenges a MapReduce paradigm is going to have comparatively. It's not going like, I mean, it doesn't have a shortcomings in such for all use cases, but in one particular use case, it really doesn't scale up very well. Then we'll move on to see the basic key characteristics of Spark. We'll also see a very high-level overview of Spark architecture. The resilient distributed datasets. This is the actual core concept of Apache Spark. I mean, your entire dataset is being held by these RDDs. So we'll spend some time in understanding the RDD. Two important operations that you can do on RDD, transformations and actions. We'll quickly see what these two are all about. And you might have heard that, I mean, Spark is more for streaming kind of application. So, but internally it has some lazy execution. So we'll see what that lazy execution is all about. All these new frameworks that are being built right now on distributed data sets, they use these directed acyclic graphs. So Spark has a very comprehensive execution engine and planner, we will say, through which, I mean, it just creates these graphs and how it executes. So we'll see how the DAG actually comes into play for Spark executions. Well, most of us will have this question about whether Spark really replaces the Hadoop distributed file system or the entire Hadoop ecosystem. So we will try to understand whether we'll try to answer this question. If it's really a replacement for the Hadoop or its related utilities. Spark also gives you different storage levels where you can persist your data, and we'll see what are the 4 major persistent storage areas that you can use while you're working on your RDDs. We'll also see some very basic tuning parameters of Spark. We'll not spend more time on it. We'll have a quick glance on Spark streaming as well. That's what it's been most popular for, and I mean, it's been right now used predominantly for streaming applications. We also will see for people who are more familiar with SQL, Spark also gives you a Spark SQL library. We'll see how Spark, what kind of attribute it has got. Another 2 important libraries for analytics, graphics, and machine learning. We'll have a very quick glance on it. And towards the end, we'll run through examples and we'll take up some questions towards later part of this webinar. Okay, all right, let's get started with understanding the basic MapReduce paradigm. I'm sure some of you would be really familiar with MapReduce paradigms, but let's see how things actually work in a MapReduce world. So if you see, the first thing it gets started is you ingest your data into a distributed file. I mean, you ingest your data into a cluster, and it gets broken into blocks. These are the blocks, and these blocks are actually distributed across different data nodes. So the moment you submit a MapReduce job to the job tracker, it gives you back your job ID, and it actually tries to see the job that you're going to run on the data set on which the job you're going to run. It just tries to find out on which data nodes these jobs should be run. I mean, on which data nodes you have these data being spread across. So it pushes those jobs onto these data nodes, and that data on that job, let's say you're running a map task, or first it starts with obviously a map task. So each map task is again applied on these input splits, and there are map functions which will take these input splits, and then produce the intermediate key value pairs. And if you have all those combiners or partitioners in between to optimize, they are also applied. And eventually things get into your reduce phase. I mean, after all your shuffle and sort has been done. So this is a very high-level view of how a MapReduce job works out. So let's see what actually the things have been there. I mean, how actually things have been characterized in a MapReduce framework. Very importantly, the first thing, obviously, it is meant for batch processing. So what do you mean by a batch processing is, so if you have seen, there is things have been actually staged into batches. You ingest you ingest your data into your platform, and then once the data is ingested, it is broken into blocks, and then it is actually distributed across different data nodes. And on those data nodes, you have a series of map and reduce tasks being applied. So everything, if you see, they are done in batches of tasks or execution engines, execution phases. So, and then you eventually have to wait until your final reducer task is, until and unless your last reducer task is completed. So this actually results into a slow execution time. I mean, it's actually, if you want to see, let's assume you have 1 petabyte of data, and your engine or your data source is producing a GB of or a ton of data which on an everyday basis, and you want to see, you want to analyze the data on it. So you just go through all this batch processing. So it at least waits for a certain period of time until a considerable amount of map tasks have finished and has given a piece of, a series of key value pairs. So there is a wait time. So your reduced tasks are little idle. Until it gets a periodic number of data, and then it just starts producing the results. So one of the major bottlenecks for MapReduce framework is the disk I/O. So if you have noticed, though we say that everything is on HDFS, a virtual file system for HADOOP, as you might be aware, but there is an underlying file system which sits on your hardware of a data node or any node in the cluster. So at each stage, it can only, it just can keep the data a certain amount of threshold into its memory, but it just needs to flush out everything. Since it needs to share this data, the map task has to share the data with the shuffle and sort has to share the data with the reduce task. So there is a considerable amount of disk flush in and flush out actually involved. And it's actually indeed majority of the processing time is spent in these disk IOs. And very key thing is, since if you're familiar with these are all distributed data sets that we're working on. So a block of data is sitting on one data node, and once it is processed, the processed data needs to be shared. The object needs to be shared across different nodes. So it needs to be serialized, so that the state of the object can be shared with different data nodes, different jobs sitting in a different data node. So there is a time required to serialize your object and then replicate it for fault tolerance. And meanwhile, when let's say you have 1,000 lines of line, or tons of lines which your job is processing, and in between you want to see a sample data, or you want to do some interactive or iterative processing, it really doesn't support. You really have to wait until your final reduce task is completed. So it's not really suitable for interactive and iterative processing. Now, if you are dealing with, I think most of us would be familiar with 3 V's of a big data: volume, velocity, and variety. And if you're really dealing with the data which has a velocity as its main characteristics, that may not be really suitable with the MapReduce's batch processing engine. Because there is a velocity which is constantly being generated. There is a constant events being generated. So what does this, with the data which has a velocity would mean is, it requires a faster processing throughput. That means you need a continuous input and continuous output should be turned around, processed, and shared across and given back to the user in a less turnaround time. And you also would like to see, when you have series of events generated in a data set, you want to run some queries, or you want to actually apply some characteristics or rules on those pieces of data that's being processed intermittently, and you want to interactively query or iteratively query the data. You require that kind of capabilities. And streaming processing, as I said, you have a continuous stream of input coming in, so you have to produce a continuous stream of output at a constant rate. So that is the prime need of a data which is being generated at a constant velocity and rate. And there is obviously a need of this data to be shared across parallel jobs who are also executing on it, because you are running an interactive or iterative querying on these data sets. So that's the prime need of data with velocity. Now let's see how Apache Spark, which tries to solve this problem, and what are the key attributes that it really consists of. And it's been there for quite some time in the market today, and it's really gaining more memberships, and there are more number of committers right now. I think it's been surpassing the Apache Hadoop, even Hadoop's number of committers. So let's see why it's gaining more popularity in today's market. Is obviously it deals on a big data tool, and it is actually quite capable of processing streaming data. I mean, data which is being generated at a constant rate. One of the key characteristics of Apache Spark is, as we have seen in MapReduce, things cannot stay in memory for a long time. It needs to. There's a lot of disk I/O involved. So Apache Spark has this kind of characteristics where it runs everything in memory. Though we will see in the next few slides that there are other ways to run the Apache Spark as well. But this is one of the most important key characteristics of Apache Spark, that it runs everything in memory. So that, and I mean, things which are there in memory, they have faster processing capabilities. I know there are some databases where, even in today's market, where things they keep the data in memory before flushing it into a log. So the processing in memory is quite faster, because your data is entirely available, readily available in your RAM. So, and we have seen one of the challenge with MapReduce is how you can share the state of the object across the board, so across different jobs. So that also it tries to solve the state of memory stored as an object, so it can be shared easily by across different jobs. As I said, it can run both in memory and disk. We will see in next few slides. So these are the key advantages that it really has got. Now, it may wonder you, if you're from a MapReduce background, and if you're more familiarity with Hadoop, that how it can really achieve all these key characteristics. We will see in next few slides. There are the Apache core, or the APIs that it provides, and the RDDs. They all actually try to do these things, try to achieve these key characteristics. Now, what Apache Spark has done, I mean, one of the disadvantages with MapReduce, the previous MapReduces, was that you need to have familiarity with Java predominantly. And I mean, there were abstractions built like, your Hive or Pig. But, if you still would like to, I mean, you cannot achieve everything on a SQL kind of language, or you cannot write everything in a Pig script. So if you want to write a concrete business logic, you should have a familiarity with Java. But there are pipes which you can even use for C++ shell. But predominantly things still stayed in Java. But what Apache Spark did, it actually went ahead, and it provided a very comprehensive support for most popular languages like Java, Python, and recently R. I believe this was added in last year's edition of Apache Spark. But R is very popular among data scientists and statisticians. I mean, if somebody is from an analytical background, they know that how R has got a very rich library support for all your analytics and statistics needs. And Scala is the majority of Spark has been written in Scala. I believe it's around 70% of Apache Spark is in Scala, and remainder is in Java and Python. So Scala is and one more language. If you have familiarity with Java, it's quite easy to build. I mean, it has various other features which actually have been inherited from Java. So this actually is a big advantage for Spark, that it can the Apache Spark can actually you can use any of these languages to build to start your building code or applications in Apache Spark. Now, very key advantage, you can always run, when you're running a streaming application, you can always run interactive querying. I mean, even in your standalone application also, you can run, when your data is in intermediate stages, you can run an interactive query on your data sets. So even despite how large they are. So, unlike MapReduce, let's say if your map phase is around 30% over, you cannot run any query on your process data sets until there is a reducer which actually aggregates the data. But unlike the MapReduce, here you can still run some interactive queries where when your data is still in stages. So everything is actually staged. So the interactive querying is supported on your data sets. And as we've been saying, streaming capabilities, yes, I mean, Apache Storm has been there for some time, but now Apache Spark has even surpassing the Apache Storm, because, you know, I mean, not only the only streaming engine, it has the other API and library supports which you can use along with your streamed processing capability. So it's obviously capable of processing streaming large data sets, and also it gives you the additional advantage of libraries and languages. And it actually, I mean, there's been a misconception in the market that Apache Spark has been built over Hadoop or any other the latest technologies, but on big data. But both have been in coexistence in parallel. But now, since Hadoop has a very well established ecosystem, Spark really complements well, and then in majority of the production and live environments, you will see that Spark is actually being deployed on the Hadoop ecosystems rather than being using as a standalone mode. Well, you may have still a few more questions, but we'll keep those thoughts towards the end. We'll try to solve those problems for you. Now, let's see what the basic. I mean, this is a very high-level architecture of Spark, Apache Spark. If you see on the top, we spoke about the language support. These are the languages it supports. So you really don't have to worry. You know, if you have written a code in any of these languages, it's easy to migrate. I'm more keen on this guy, the R, because, you know, it has a very comprehensive support of all R libraries, and it actually interfaces very well. So you can do a quick statistical analysis using your R interfaces. Python, it also has a very rich support. I mean, Python, majority of Python's popularity lies with the Lambda expressions, which is a new thing, but I think now Java 8 also has introduced them. So Python also, it has a very good support, and obviously it has a very rich API built in on API support for Java. And the basic Spark shell that we invoke is actually in Scala. So Scala always remains the core language for the Apache Spark. But it's very easy to grasp. I mean, there's no big syntaxes that you have to learn, but Scala is also a very easy to crack language. Now, underneath these languages, you have different libraries, a very rich library supports that you can see the stack of libraries that it has got. Like Spark SQL, you have Spark Streaming, the machine learning libraries, you have GraphX, and you have packages which for the additional capabilities. The data frame API is mostly meant for, you know, if you have a structured data and you want to run some SQL queries, it also gives. Data frame API is also a recent addition to the Apache Spark. I think it's almost a year old since this been added. So data frame API is also, the API is also a recent addition. And then the heart is the Spark core, which actually interfaces with all these storage engines, your storage handlers. You know, it can deal with any type of data set that you have. Now let's see in detail what the architecture actually speaks about. So if you're familiar with any of these languages that we have seen earlier, it's actually quite easy for the migration. I mean, it makes your eases your Spark adoption and development process, and all have been quite easy to understand languages. Now, we spoke about data frames. Let's say if you have a data set where you can you know, define some schema for your data set, like, you know, you define a schema saying that my first column in my data set represents an ID, a string, the second column represents a float, an age, or I mean anything. I mean, so if you can kind of attribute a schema to your data set, this can be transformed into a data frames, and it's quite easy. I mean, once you have defined your data set, it's just one function call transforms your entire data set into a data frame. And once it's been transformed into a data frame, data frames are actually are like structured columns, just like your relational tables. And if you see a relational database table, so it just transforms your data set into a structured column, so that, you know, now once you have a structured column data set available for you, you can run SQL-like queries. And most of those SQL queries are similar to the actual or any relational database SQL queries. I mean, the syntax remains the same. So this is quite popular among the business analysts who run day in, day out some you know, operational reporting needs, to address their operational reporting needs and to do some quick analysis on your transactional data. So, so once you transform your data set into a data frames, these guys can apply their their existing SQL queries on the similar data set on Spark for a quicker processing. Spark, in addition to language support, it also has a very vast support for various type of storage systems. Now, Spark can run in variety of storage systems, like as we have shown in this image, that you can actually have your storage system as your Amazon S3 or a Google Cloud, or even a Hadoop cluster. And it can also obviously run on your local file system as well. You can still use your local file system. So as I've been saying, that Apache Spark is not a part of Apache Hadoop. It both has been in coexistence for quite some time. So you can even use your local file system. You can use your local file system to run your Apache to run any of your Apache Spark programs, and you can even parallelize them in your data sets to have a virtual cluster kind of setup locally. So, but in production environments, as I said, you can always use a Hadoop cluster as a storage engine, or a Google Cloud or Amazon S3. All can go well with the Apache Spark. And typically in production environments, as I said, the Spark is not managed like a standalone system. It is managed through Yarn, the latest Hadoop's new framework, and Zookeeper, which actually kinds of tracks your all nodes and it manages your entire cluster. And the Mesos is your resource manager. In fact, Mesos has a very integrity. It's actually had a very combined history along with the Apache Spark. Both have been developed along with the same projects, and Mesos now is a different project, and it's in some of the production environments, it's very widely used to manage large resources, and it even manages your Zookeeper as well. And it also it's so intelligent that you can based on your request, it actually knows which kind of resource it has to produce. Like if you're actually writing an HBase query, you're trying to get a HBase data. It just sees the data request and it allocates a resource, HBase resource to you. So it's a very advanced resource manager. So Spark's architecture, primarily, as I said, storage it can support any type of storage engines, and it's really very good. I mean, you really don't have to worry about adding additional interfaces or writing additional wrappers to integrate these storage engines into Spark. So it has a very readily available APIs. Under the hood, they take care about your storage mechanisms, respective of whichever storage you're going to add to process your data. Now, Spark Core is the actual main component in the entire Spark architecture. This is the guy who is responsible for, scheduling your jobs, rearranging your tasks, regrouping your tasks into stages, and interfacing with your storage engine, interfacing with your APIs like DataFrame API or any libraries that it has got. And actually, it interfaces with your storage engine, and it is the one which is actually directly speaks to your resilient distributed data sets. And this is as I said in the beginning of this presentation, the RDDs are the variables or the objects which actually holds your data. So they are like they abstract your data and then represent you to you in one object or a variable. So it is. I mean, this is the one which actually interfaces with your RDDs as well. Now, each of these Spark libraries that we have seen are meant for one specific business use cases. So we always think that Spark is only meant for streaming, but no. I mean that is one of its key USP. But Spark streaming, obviously, we know it's meant for processing for a continuous input and output data. In addition to that, the Spark SQL interface is for the people who are from the SQL background. We have been living in a relational world for quite some time, and this will continue even for next few generations. So we cannot get out of the SQL world. So Spark gives you a very rich interface to support all SQL-like queries. And as I said, the moment you transform your data into a data frame, you can just run through your SQL queries on this data set. So it's a very seamless transition that you can get transition for your data sets to be transformed into a SQL to be transformed into a structured column-based data sets. The one advantage that Spark did This is in today's world. We know how much of importance analytics has got. If you really see big data, I think majority of the population thinks that the big data is only meant for processing. But once the processing is done, what is next? Actually, you need to think about what you need to do on a process data set. So the obvious things that you will do is you want to describe your data set, you want to predict what patterns a data set has got, and prescribe any measures. And that's the quite big use case in today's world. So the machine learning libraries that been there for quite some time, but none of the Apache frameworks which are built for big data use cases have not introduced anything on statistics or analytics. But Apache Spark was quite intelligent, and it just built many library supports, many machine learning library supports for statistical and analysis and machine learning. Now, it has a very rich support. When I said about on the Apache, on the machine learning, it actually supports your correlations. It supports your aggregations. People who are familiar on statistics and analytics may be able to correlate these words. But there are some very good frameworks and models, like decision trees. All that it has a built-in support. So to just like an R, which gives you all these libraries, it gives the Spark gives you all these machine learning libraries readily, where you can, and then you can give an entity to it and process it, and you apply your algorithm and you get back your results. So under the hood, it can still use the Spark's in-memory capabilities, and on the wrapper you just use those libraries to run your jobs, or to produce the analytics on it. Now, GraphX is one of the very important analytical, or I will say, kind of database. If you see a Twitter, right? For example, if you have a Twitter feed, how does that Twitter data would look like? Let's say you have one node, which actually, and let's assume this is one tweet. It gets retweeted, and it is followed by someone else. It is just again retweeted and followed by someone. And this guy might be following the same tweet, and then there could be another guy who might be following his tweet. So there is a kind of graph which you would see. This entire set is like a graph. You have one node, there is an edge node, and edge node, and each of them might be correlated in some other way. There could be another node, and this guy may be related to this guy, and this guy may be related to this guy. So this guy may be following this guy. So this is a graphical graph database, it's called. So again, Spark was quite intelligent to see the importance of GraphX. And most of the social networking feeds, or social media feeds, or as I mentioned here, one of the most important thing was the implementation of PageRank. Now, how does a PageRank look like? Is like originally when Google was dealing this problem in around 2008, I believe, where they were trying to see how do they rank a page. Based on that rank, they actually give the result back. Let's say you searched for Spark on the Google search engine. So there could be millions of pages it will just crawl through. It just crawls through the web and finds it. But how does it know that which one should be shown on the top and which should be shown in a chronological order? So that's where it actually does a page ranking. So for example, these are the pages. Assume these are the pages which contains the keyword called Spark. But might be this guy is the topmost guy which has more visitors. Like there are more visitors it has got. So the ranking changes for it. So maybe this is another graph which it has built. So this page gets more ranked. So similar kind of data analysis you can do on Spark, because there is a built-in library called GraphX to do a page ranking and any other graph data type based analytics. Spark R, as I said, it's a recent addition to the Spark package, and it's very popular among data scientists and statisticians because it has a built-in support for all statistical models, and you can do many things. You can just do a sampling of your data and then run through some of these statistical analysis. So Spark has a built-in support for R. So that R is a programming language again. So it has a built-in support for all those APIs of R. Now let's quickly see what is our, the resilient distributed datasets. It's abbreviated as RDDs. The RDDs actually are your fundamental blocks. They are like immutable atomic data sets, which actually contains your data. I mean, I wouldn't say contain, but just actually points to your data set. So it is the primary abstraction of your distributed collection of your items. I mean, the resilient distributed data set, if you know, in the big data world, everything is actually distributed. So when I say it's actually distributed, let's say your file this is your file, and you have one file, and it just gets broken into partitions, and this file is broken into partition, and each of these partition is stored into different node. So this can be one node, this can be another node, and this can be on another node, and this can be on another node. So if you see this example, I'm creating a variable called my file, and this is called Spark context. I mean, everything is stored on one variable called Spark context. Then the moment you spin off your Spark shell, and I'm loading a file called Spark file.txt. Now let's assume this is your Spark file.txt, and it is actually broken into partitions. These are the partitions. This is one partition. This is another partition. So these are the partitions where it is actually broken. So these partitions are actually stored into different nodes. So what Spark does is, based on these partitions, it actually, and these all partitions are actually distributed objects. So when I create a variable called my file on this file called spark file.txt, it just creates an RDD called my file. So this entire grouping is actually stored into a file into a variable called my file. So this is your first RDD that you have created now. So this my file is actually stored as an RDD. So if you see, it's a parallel distributed object. My file, you can treat this as a parallel distributed object where you based on your where is created on a file called sparkfile.txt, which has again partitions. So in a layman's term, a partition is actually a logical breaking. So if you are familiar with your actual Hadoop terminologies, let's say if my file can be broken into blocks B1, B2, B3, B4. So similarly here it is actually broken into partitions, and these partitions are again spread across different nodes. So for an end user like me, if I'm just creating a variable called my file, so for me my file is an RDD, but internally it is actually pointing to four different partitions which are on different nodes. It's been spread across, but the RDD remains as a immutable object. Each RDD remains, and each RDD has performs an atomic transaction. So as I said, this line creates a RDD called my file. So this file, my file, is again split into different partitions. Now, each RDD maintains a pointer to one or more parents along with metadata. So what does it mean is, now first RDD which I created, so let's see the example. So in our first example, we created an RDD called my file. It's called sparkfile.txt, and then we created what we did. Now what we are doing is we're trying to filter a line called Spark in this my file. So this is my second RDD. So what actually Spark does is, now you have series of RDDs created. Now this is your first RDD that we created in our first example, and then we went ahead and created another RDD called lines.spark. So this is my second RDD. This was my first RDD. Now I can create one more RDD in another line, and then it creates another RDD. So each time it maintains a pointer to the data set, and what it does is it just creates a lineage. So what a lineage means is it creates a relationship, right? Now if I want to trace back the actual source, now let's even see this example where I'm saying text file, I'm running a transformation. We'll see what a transformation very soon. So I'm running a filter transformation on this to find a line called Spark. So what it says that it says that the parent RDD, the metadata information for the parent RDD is here actually. So this is the lineage. This is the lineage we're talking about. These are the lineages that it is building. So it kind of creates a relationship and a kind of graph which represents your entire chain of RDDs, how they are grouped together, and how you can actually get your data from your parent RDD. So one advantage with the RDD is, unlike your MapReduce jobs, where when you create your MapReduce job, when you create writable objects like text writable or any writable object, it actually gets the data in. But in this case, it just maintains a pointer, and it doesn't actually load the data. So even you created a RDD called my file from the file called sparkfile.txt, it just creates a pointer. I mean, it creates a pointer to that file called sparkfile.txt. And what this actually helps is, in case of any unforeseen issues, where let's say you have network failures or any other cases, it helps in keeping it fault tolerant. Now, what does a fault tolerant means? I mean, it can actually track back this lineage to reconstruct your RDDs and get the data back. And these pointers actually are not holding the data, so your original file still remains safe. Now, on the RDDs that we have created in our previous slides, there are two set of operations that you can do on your RDDs. They're called transformations and actions. Now, for example, the one we have seen called the filter. Filter is one of the filter function that we have used. Is one RDD, one transformation that we applied on the RDD. And on the same RDD, we have applied another transformation where we are trying to see the lines with, we're having the keyword called Spark. So there is a group of RDDs that we are creating, creating lineages, and each time it's creating a pointer, and it is constructing a lineage and an information about its parent. So these transformations are actually applied on an RDD and to transform your data based on functions that you supply as transformations to your original files. Now, the one thing that we should notice in this case is the original RDD always remains same. You don't change your RDDs. So we had two RDDs, as we have seen here. The my file. If in our previous example we had one RDD called my file and another RDD called lines with Spark. So each guy has a pointer to this. And this guy will never change your previous RDD. It is just maintaining. So each RDD remains immutable. I mean, it's actually cannot be changed. So the original RDD always remains unchanged. And what it actually a very interesting thing called directed acyclic graphs, which called DAG. So it maintains a graph of all these transformations from first to your last RDD, and everything is actually logged into your DAG. And this is the one which gets actually persisted and shared across different nodes or stages where your actually task scheduler is running. So it doesn't. So what it does is, as we have seen here, this is the graph it has constructed, and it shares this graph. It persists it into a file or in some way, and this is the one which actually gets shared across your different partitions. So we have seen in this case, these are the partitions. So when your scheduler is running your job, this is where it actually your scheduler schedules your stage. I mean, it will just group them into a stages, like based on number of partitions that you have got. So it stages and it runs a series of tasks. So when it is running those series of tasks on these partitions, maybe it is running a task here, it is running a task here and here and here in all these nodes. So what it does is it actually sends this DAG information to this each stage where your job is running. So it is just sending this DAG to these stages, and that DAG is actually executed on your job. So the DAG tells the scheduler, or these are called worker nodes, by the way. I mean, these are all, each is called worker node, just like your data nodes. These are called worker nodes. So the scheduler, based on your partitions, it creates stages of jobs, and each stage can comprise of different tasks that it can run. And again, the tasks are based on whatever transformations you apply. So these tasks are actually executed based on the DAG that you supply. So it is, I mean, everything is logged into your DAG. Now, what is the advantage of DAG is, in the event if you have a network failure or cluster failures, or if there is a loss of data, you can actually trace back your DAG because as we know, we know how this entire transformation is performed. So you can trace back this DAG to actually reconstitute everything back. So you have actually a kind of metadata info available for your job execution. So that's actually an advantage which RDDs provide you through these DAGs, that you can, for a fault tolerant ecosystem it builds through these DAGs. So one of the few, there are many map and transformations that we know, but most popular ones like the map transformation. It is as we have seen in previous case. Let's say this example in which we are applying a map transformation. We can draw an analogy from the mappers from MapReduce job. So when you're running a map job, you apply a certain business logic. Let's say in our case, business logic is I want to split each line that's from comma. So I want to just tokenize each line using the comma delimiter. So what map function does is it actually splits the line of each file with comma. So it actually, again, this is again stored into a RDD. So that's why it says it returns a new distributed data set formed by applying the map function on each of your elements. The filter function, as we have seen again in our previous example, it applies the function, whatever function we have specified. In this case, we are saying that I want each line that contains Spark. So it just returns through those lines. We will run some of these examples in the lab towards the end of this presentation. So this is just a high-level view of how transformation looks like. Now, similar to map, there is a transformation called flat map. Now, what the distinction between a map and flat map would be is the flat map returns you an iterable set. So when I say iterable, so it can return when I apply this function called func, or in this case, let's say I'm applying a function which splits the line or tokenizes the line based on a white space. So it gives me back an iterable set, just like our reducer, where you have a key and a set of values to it. So it returns me a group of output items on which this function is applied. So a sequence rather, I would say. So, but in the map, it doesn't give you a sequence. It is just an individual elements that it returns. Sampling, again, if you want to run some of your application, or you want to just generate some data on a sample of data, it just uses this fraction of data, and you can do some of the sampling with this replacements. Another key transformation is group by key. This is very similar to a relational SQL statement, where let's say if you want to group by certain column, it's very similar to that. So what group by key does is, let's say you have different keys. Let's say now I have 1, 2, 3, and again I have 1, 2, and I have some elements like I have X, and I have A, and I have B, and again I have some. These are my elements, and E. So when I run a group by key on this transformation, so what it does is it groups the similar keys. So the similar keys in this case are 1 and 2. So it just groups them, and it will just end out after this. It will just say 1, and it has X, comma, and we have some A or some variable. So it just returns this variable. So it will just group them together. So after my grouping it, I have 1, X, Y. Similarly, 2 will have A, E. So it is just grouping a similar key together. Now, reduce by key is very similar to group by key, but in this case, what it will do is it will just add X plus A. So it will after applying the reduce by key, you will say 1, X plus A, similarly 2, E plus Y. It is just like your reducer in the MapReduce jobs. Now, before we move on to actions, I would like to say some very interesting facts about these transformations are. There are usually 2 types of transformations you see. They're called narrow transformations and wide transformations. So what is a narrow transformation does is, if you go back to our previous examples called flat map, map, or filter, where these functions can work on your individual partitions. Now we know that your data is actually split into partitions, and each partition is actually run on a worker node. So whatever data is available on that locally on that worker node, these map functions can run on those functions. So it doesn't need, it can run independently. It doesn't need a data transfer among different worker nodes. So those transformations, what Spark does is it is very intelligent. It groups those transformations together, and it actually runs them locally. So they're like narrowing those transformations. So all those transformations when you're running on map functions, like map, filter, and flat map. So these transformations doesn't require a data transfer among different worker nodes. So they can be run on individual nodes. So when the Spark execution engine, like the scheduler is running, creating stages and tasks for these transformations, it will just keep everything narrowed, and it can run locally. So these are called narrow transformations because they can run on your local data sets. But when you talk about these transformations, like reduce by key or group by key, now let's assume the 1 and 2 are on this set is on first partition, and let's say this set is on second partition. So it needs the data to be transferred here before it can run these reduced transformations. So that's why these transformations require certain shuffling and sorting. It needs to shuffle and sort, and then it moves to the data. It needs to transfer the data sets to the first node. So these transformations are called wide transformations. So they need certain shuffle and sort phases. So that's how the shuffle. I mean, as we have seen in the MapReduce example in the beginning of the session, the majority of time it spends in data sharing and data IO, disk IO. So the reason for the disk IO is it actually it has to group the keys, share it across the network, and then push the data to the reducers. So there is a certain IO involved. So what Spark intelligently does is it actually groups these transformations into two stages, two types, whether it needs to do a narrow or a wide transformation. So in case of narrow transformation, there is obviously it can save some network IO and do things locally. So that is the advantage of narrow and wide transformations, which I want to highlight here. Now let's move on to the actions, the second operation that we can do on an RDD. Now if you have seen in the previous case, like transformations, they just produce an RDD, but there is no result associated with an RDD. So the moment you create an RDD, as I said, it just creates pointers to your data sets or to your variables, but it never actually gives you a result back. So let's say you did some filter transformation and you said, I want to filter each line that contains Spark. So it just creates a pointer, it creates a DAG, and it just stores it, and it doesn't give you a result back. If I want to get a result back of it, I need to run an action on it. So I should run an action on it so that I can get some data set. So I get a result back out of it. So what actions will do is it just it actually executes your transformations and it evaluates them and it produces a result. So again, similar to RDD, it doesn't change your original data or it doesn't change your data sets. So this is very important to make a note. The actions usually don't change your original data sets, but these are the ones which actually execute your DAGs. It execute your transformation and give you a result back. So again, very similar to transformations, we have very common actions like reduce, which will again, it just aggregates the data based on the function. Function is nothing but like a business logic that you want to write, any business logic. So that actually runs these logic on your data set and it gives you a result back. Now collect is something very, very often used, but it is often used on smaller data sets to get your entire result back and show it on your console. So if you want to collect your entire, let's say you have RDD which is doing a map and it is doing a filter and then it is doing a reduce, and then you want to collect the final result to see how your data looks like. So it just collects your all data sets into one and just shows you on the console. But more often this is not used in production environments or large data sets because that requires a lot of under the hood materialization. So you need to get all your data sets, transform RDDs, and do those aggregations and then show your result. So you essentially are kind of losing that parallel distributed computing characteristics. Count again, if you want to see how number of elements in your data set, and then first, let's say you just want to see what is your first element in the key in your data set, and or you want to see the n elements in your data sets, and save as text file. Very similar, I mean, very descriptive in itself. Like it just saves this text file to the path that you. Count we talked about, and the save as text file path. So again, remember the actions are the one which actually gives you a result back. So if you the transformations are just pointers, or they are like creating an execution plan on your data sets. So they don't really see they don't really give you a result back. Very interesting. Yes, Spark is lazy. I mean, we all been thinking that Spark is the guy who runs everything in memory, and it produces a very fast result. Now, before we actually talk about lazy execution, I think most of us are familiar with with Facebook. How does a Facebook actually show the data? So when you log into your Facebook, on your wall, the moment you scroll, it just shows up, let's say, 10 wall messages, and then you scroll down, it just again loads those another 10 wall messages. So that is called a lazy loading or lazy execution. So that is very similar. What Spark does is, so the moment you created those RDDs, they just contain pointer to your data set, and they just create a plan and a pointer. So they actually don't, there's nothing actually evaluated. So, but the moment when you run any of these actions, let's say in our previous examples, we had some RDDs. If you look back our RDDs, and then I just created a file, and I just applied some filter to it. So now I just applied, let's say I created a file, and then I applied another transformation called, I'm trying to pick up lines with Spark. And again, I want to, let's say, apply one more transformation, and I want to split the line with containing a comma. So until and unless I execute an action called collect, there's nothing executed. I mean, there is no, the DAG is actually not executed. It just creates a plan, and it just stores it somewhere. But the moment I execute, let's say, a collect, so this is like a scroll. When you do a scroll on your Facebook wall message page, when you scroll, that means you're triggering the Facebook server, telling it that, hey, I need another set of 10 wall messages. Now I scroll down, I need some more 10 more messages. That is similar to what Spark does. I mean, the moment you execute a collect option, that's where you're telling the Spark framework that now I want results. You go ahead and execute this. I mean, you go and execute the RDDs that are associated, all lineage of RDDs that are associated with it. Similarly, if you run a count, first, taken, whatever, I mean, whatever action you run, that triggers the Spark to execute those RDDs. Now, that's what it means, that nothing is evaluated when an RDD is really assigned with any transformations. So all these transformations are lazily evaluated when a subsequent action is actually assigned to it. Now, what is the advantage with this is, it actually improves your performance. You can create tons of RDDs, a lineage of RDDs, and unless you specify an action, you are not actually processing them. But in case of batch processing of like a MapReduce job, what you see there is, you created a MapReduce framework, and you are actually running everything. I mean, let's say you have a job that runs every day to pick up 10,000 lines of code, 10,000 lines of data set, and then you actually reprocess your entire data warehouse to augment these 10,000 lines, and then you run a map job on it, you apply your business logic, and you produce some concept or KPI for it, and then you actually show a result to the end user in a reduce phase. But maybe the end user is only looking for today's data. So when you're looking for today's data, you are only actually looking at certain fields in that data set. So, but what it has done is, it actually has processed 1 petabyte of data, assuming that that's your size of your data set, and it actually redundantly did all those processing things. But unlike that, in this case, unless, I mean, my the execution is based on my action that I specify. Let's say if I want to run only first 5 lines, like we have seen in this previous example, I just want first few lines. So it will just process it and give me it knows that the action says that it needs only first line, or it needs, let's say, 5 n number of lines, say first 5 lines. So it knows based on your action, it knows how much of data it has to process and the DAG that it has got. So that's the advantage with it. So the performance can be improved by avoiding any unnecessary processing of the data. That's what it means to say. Now, but it sounds really interesting, but they can be can also be a cause of concern with respect to bottlenecks. Why I mean a bottleneck is, let's say you have 10 RDDs who are created, and you created a lineage. One of the RDD, you have applied a very complex RDD which requires a lot of internal processing. Now, assume you have a 10 node cluster, and each node is sitting idle at this moment because you just created an RDD. You just created a lineage of 10 RDDs, and those lineage 10 RDDs, among them, let's say 5th and 6th one requires you a complex processing or execution time. Since you just created transformations, nothing is executed, though you have idle CPU times available across your cluster. But the moment you apply an action, assume that there are another 100 more jobs which got triggered by some other users, and now the idle CPUs are consumed by those jobs. So now, though you had time though you had enough CPU cycles when you were creating those RDDs, they were never executed until you have triggered an action to it. So that's why it can sometimes lead to a processing bottleneck, because you are actually waiting on a command called action to actually run or execute your DAG. So that's what it means. I mean, in some cases, though you may have resources available, but you don't execute or you don't utilize those resources until you specify an action to it. So that's why some cases it may be a bottleneck, but again, it depends on the use case that you're using it or running it. Now, this is just a graphical representation, visualization of how things work. So as I said, you apply transformations on each RDDs. So this becomes a lineage of RDDs. So there is a lineage created. And on these lineage of RDDs, you perform an action that gives you a value or result back. So only when an action is executed on an RDD, when an action is performed in RDD, the data sets and the transformations are executed. Now, very interesting thing about Spark is, and most of the recent frameworks, even like Apache, just similar to Apache Spark, we have Apache Crunch also, which also uses this internally. What the new editions of these frameworks they were doing is they create a planner or an execution plan before they actually run your jobs. So what directed acyclic graph does is, it is an execution framework for, obviously, as I said, for distributed data sets. So when you have created, like we have seen in our previous example, that we have created different DAGs, which have, we have created different RDDs that we have created. So each RDD will contain a lineage towards its parent RDDs, and the parent RDD would contain a lineage to another parent RDD. So it creates a kind of graph which tells that once a user submits an action to the scheduler, so it knows that the graph is already available to it, which actually explains the execution plan, and that graph is called directed acyclic graph, and this is the one, as I said, is submitted to your different stages, different worker nodes. So the DAG is the one which is submitted to your worker nodes, which tells the execution plan to it. So the moment an action is performed, the graph is submitted to the DAG scheduler, and then the DAG actually divides these operations into stages of tasks. So as we have seen in our previous example, that we have one block, these partitions, we have different partitions, and these partitions are broken into different nodes, worker nodes. We have one worker node, we have different worker nodes being split across. So when the moment each DAG is actually submitted, so each DAG is submitted to each of these. Each DAG is submitted to each of these nodes, and on these nodes, these DAGs are executed. So what actually it does, based on your partitions, I mean, these are the partitions that you have 1, 2, 3, and these partitions, based on your partitions, there are stages created. So let's say this partition works in stage 1, this in stage 2, stage 3, and also based on your transformations, because you know your DAG, you know what actually is your transformation. It actually knows, let's say I'm only using a filter and map and flat maps, filter and maps and flat maps. So it can actually run them together, and it can only run them based on your transformation that you apply, the narrow or wider transformations. So based on these DAGs, it actually runs those transformations, whether it needs to do a narrow transformation or it needs to do a wide transformation. And finally, these stages are executed, the tasks are executed in stages on narrow or wide transformations. Now, as I said, again, each stage can contain a group of tasks based on the transformation that you have applied. And these tasks are again based on your partitions of your data input data set. So what this means is the pipeline is, what I mean to say, is through narrow transformations. It can actually pipe together those transformations together in the same data set to do the DAG execution. So for example, as I said, the many map operators that can be scheduled in a single stage, because they all work on your individual data sets. They doesn't require you to do a data transfer. You don't need a transform data to be transferred from different stages. So if you really break down your data sets, it is actually a partition. Each partition would contain a stage, and each stage can contain a task. So, and each task again can be grouped on your DAG. Each task can be grouped based on your transformation that you're applying. So if you really see this is one of the DAG graph that we are looking at. So these are the nodes, which each node can be a transformation, like map, collect, filter, reduce, sort. It can be a transformation or action, I mean to say. And these edges actually specify, these are the edges, these are called edges, which actually tells you what is your lineage of that RDD. So when somebody actually performs a collect, so it knows that how the lineage can be established to this graph. It can get quite complicated. Sometimes you really don't have, and in practical world, you really don't worry about the DAG, because that is something which is meant for the framework to understand. So sometimes the DAGs can be very complicated, like this one, where from each data set you created a series of DAGs. You have the nodes, you have edges, and how an action can result. So for example, in this case, I'm doing a collect here at this stage. So I know that I just have to create this lineage, and I can execute this graph. I don't have to traverse through the entire graph to get this at this stage. But if I want to do a collect at this stage, I may have to traverse through all this. Maybe it's saying that I performed the first transformation map, and then second transformation map, and then I did a sort, and then I did a collect. So, or I need to do a filter, reduce, and collect. So it is quite complicated, but this is a DAG which is actually will tell you what is your metadata about, it tells you a metadata information about your execution plan. And at any stage when action is performed, this metadata info about your execution plan explains you how it can execute to get you a result, or to actually execute an action on it. Again, you really don't have to worry too much on how a DAG is represented, but you can obviously see a DAG. I'll show you in the lab how we can actually look at the DAG information, just if you're curious to know that what was the execution plan. In some cases, let's say you're trying to optimize your programming model, and you want to see that where maybe you can feel that you have created a model which does 2 maps and then sort. So you can actually, once you see a DAG, it will tell you that there are 2 maps that you're running here, and then before you do a sort, maybe this one is a redundant. I can actually eliminate this. So for your performance optimizations, you can look at these DAGs and see what can be eliminated, or to understand how framework is executing. Because the moment you execute your action, you might have created a series of transformations already. So you can feel that There are certain transformations which are redundant, you don't need them, or maybe certain transformations are not optimally designed to do before you do an action. So all that information you can understand through this DAGs for your performance optimizations. I mean, that is one use case which I can think about for the DAGs. Very interesting question again. We will try to answer this very soon. I mean, most of us will be feeling that, you know, yeah, Spark has got many. We have until now we have seen various advantages of Spark over MapReduce. So that brings up this question that is Spark is really, I mean, is Spark a replacement for Hadoop? Yes, I would say it's not. No, I will deny it. The reason for that is, see, it's not a replacement for neither Hadoop ecosystem or MapReduce, because each one is meant for a different use case. Now, but as I said in one of the slides, that indeed Spark can really use the Hadoop cluster management and HDFS storage. Now you see Hadoop has really evolved over many years. Now there are many big production environments. They have been set up on the data centers which have been built on the Hadoop clusters, because it really has an advantage. It is very fault tolerant. It has a good fault recovery mechanism. It has a redundancy, there, so low latency. There are a lot of advantage that the Hadoop clusters have got. So indeed, I mean, both can benefit together. So for example, as I said, Hadoop framework is very capable of doing a faster recovery of data from data nodes. So that's the advantage. And as you know, the data is distributed across different data nodes in Hadoop. In the Hadoop exactly. So you can deploy your jobs across the cluster and run. So your partition data is readily available to you. So you don't really have to parallelize your jobs. So as we have been seeing that your data file is actually split into partitions. So as I've been saying, that your file is actually split into partitions. Now you need to split this file by parallelizing your job. So you really don't have to do that in case of Hadoop, because the file is already broken into blocks, partitioned, and stored into different data nodes, and then you can directly run your Spark jobs. Similarly, the MapReduce drawbacks that it has got, like the library support it doesn't have for GraphX or MLib or R. So Hadoop can actually take an advantage there. And also in some cases where you really don't need a batch processing, you need a faster throughput, so it can use Spark as well. So to actually summarize on Spark versus Hadoop, we know Hadoop, I mean, in general, we're talking about MapReduce here. It is more suitable for batch processing. Remember, Spark is not very capable of doing a batch processing kind of data, because this is only meant for velocity of data. So, I mean, assume you have 1 petabyte of data. You have 1 petabyte of data that you're processing, and you want to do a streaming on it. I'm sure there is no such system available in today's world which can actually hold a 1 petabyte of data in memory. So you obviously would like to do a batch processing on it. So on those kind of use cases, where you have high volume of data being generated, and you don't really care about, or you don't have a concern on execution time. So that's where you can go with the MapReduce in Hadoop. But on contrast, as I said, if your prime need is to do a real-time streaming analytics or streaming analysis, processing of your data for a continual input and outcome of your data, then the Spark really scores well there. So different use cases, different applications has different use cases, and you need to choose among one of them based on the use case. So as we have seen, one of the key characteristics of Spark is how you can store your data. I mean, we have been talking all the while that data is in memory, but as I said, in some of the cases where your data, I mean, if your data can really fit into memory, you obviously can go with memory only option. That is the default storage level that RDD has. And as I said, if it's not too sizable and it can fit into it, you can leave this option as is, and memory only it can fit. And obviously, since everything is available in memory, it is more CPU efficient, and you can get faster throughputs. But one disadvantage with this is the objects are not serialized. So that means you cannot share them across other jobs over network. So you need to first serialize them and store. So they are deserialized Java objects which are stored in JVM. The memory and disk again, if you often feel that your entire data set cannot reside in memory and it needs to be flushed periodically into the disk, then this you can set this option memory and disk. So it knows that at certain threshold it needs to store the data on disk, and again this is deserialized. If you want to take an advantage of memory and serialized objects, so this is the option where you can fit the data into memory and it's a serialized object. There may be little overhead in serializing your object, so there could be a little delay in your processing. So it depends. I mean, if you really don't care, let's say if you have more narrow transformations and you don't need to share your object very often with other jobs, you can still use memory only and serialization. I mean to say, beg your pardon, you only need to use memory only because you don't want to serialize your object and you don't want to spend time serializing your object. Memory and disk serialization, this is the one where very similar to the memory and disk, where you can store your data into disk as well, but in serialized form. So Spark tuning, but in most of the cases, as I said, the data is distributed, and obviously your jobs need to talk to each other, and the nodes need to speak to each other if you're doing an interactive or iterative querying. So it's recommended you serialize your RDDs so that the object can be easily shared. Parallelism, yes, often there is a default parallelism being set, so you can obviously parallelize it, but again, if your data is already parallelized and stored into different nodes, this can be avoided. But what advantage with this is your data is actually broken, because again Spark can run standalone or in a cluster mode, but most of the cases, let's say you're doing you're processing a large data set and you don't have a cluster or anything available, it's recommended you do a parallelism so that your data is partitioned, and once the data is partitioned, it can run parallel stages of tasks. It can run stages and parallel tasks on a similar data set, and the framework will take care about whether to use a wide transformation or a narrow transformation, but it will increase the parallel reduce tasks as well. Garbage collection tuning, I think people who are from Java background will know that this cannot be obviously a very big bottleneck, because the default garbage collections sometimes can create a lot of bottlenecks. So you can tune this garbage collection in the Spark. Data locality, very similar to, again, MapReduce framework, where you can actually create local data sets and you can specify the Spark locality attribute to tell the Spark how much local data can be executed. All right, now let's get into the most important thing on Spark. It's called Spark streaming. Spark's the biggest advantage, and the reason why it has got such a wider acceptance in the market is because of its streaming capabilities. Now, what it does is there is something called this. It is purely based on a concept called micro batching. Now, the moment you receive a data set, so what it does is it actually breaks the data sets into input of batches. It's called micro batches. On these micro batches, the Spark engine runs your actual business logic, whether you want to do a transformation or an action on it. So the first thing it does is, the moment you receive a stream of data, you break the data. So the first thing it does is it just breaks your data into batches, and then so first thing is the batch it does, and then you specify the time interval. Let's say I mean there should be a logical end to your batch. So what you can tell is I will like to get a data in 1 second interval. So I'm trying to see, so because when you say streaming data, let's say you're actually trying to stream a sports event, and that sports event is spanning across 3 hours or 2 hours of time frame, but you don't want to wait until that 2 hours of time frame is finished. You'll say that every 5 minutes of stream data I want to analyze. So you can specify your time interval as 5 minutes. So I will say this is my time interval. So these batches are created based on this time interval. So you will create batches of jobs, or your batches of input data into these 5 intervals, 5-minute interval. Now each of this interval batch is actually is called we will see very quickly, it's called D stream. Now what does a D stream mean is, you have a stream of data which is very continuous, which is a continuous stream of data, but it is discrete. So each block is discontinuous. So it is only based on an interval of time you are picking up this data. So let's revisit it again. Let's say you have an input stream of data which can span to 2 hours, and you are specifying a time interval of 5 minutes. On these 5-minute interval, it is building a batch. It's called input batch. So micro batching, which that I said. And this is the batch of jobs. So this is the entire batch that you created. On this batch of jobs, what it creates is a dstream object. Now let's say your interval is finished and you have a window which is finished, a window which is already, you're looking at a 5-minute window, and in that window you created batches of these stream objects. So these discrete objects, they all are stored under dstream. So this is one object which contains a continuous window of objects. Now each internally, this will be again an RDD. So underlying implementation will be an RDD. So there is an RDD created, but they are in batches, micro batches, and they are not continuous. They're like discrete, but you are grouping them together under a dstream object. That is something that's called discrete object. I mean, that it's called discrete streams, which is, I mean, the actual English word for discrete is not continuous. So a non-continuous stream of objects, which again are stored as RDD under the hood. So once you have all a discrete object, that's where actually you submit it to your core Spark engine, and you can produce batches of batches of processed data, and you apply transformations or your actions, whatever. I mean, the basic 2 operations that you do. So because under the hood it is still an RDD. So that's what I was trying to explain here. So Spark streaming is obviously an extension of your core Spark API, and what it actually does is it actually receives a continuous live input data streams, and it divides the data into batches, as I said. So this is called micro batching, and these data batches are actually fed into your Spark engine to produce your final stream of results. Now, though this is what the high level abstraction it's called discretized stream or D stream, which actually represents on a time interval, a window of time interval, how many blocks of data you've got. Those blocks are actually grouped under D stream. So as I said in my previous slide, D stream is represented as a sequence of RDDs. So they are again under the hood, they are RDDs as well. They are RDD in itself. Let's quickly see what a Spark sequence is. So let's say you have a data called myfile.csv. I mean, you have a CSV file, and I'm just trying to, this is again Spark terminology, sorry, I beg your pardon, it's a scalar terminology. You are trying to associate a schema to your data set. You're trying to associate a data set to you're trying to associate a schema to your data set. Let's say I'm saying my first column is an integer with a name called ID. My second column is a name of data type string, and my third column is pin, it has a data type called long. Now, once I've associated a schema to my RDD, so my file is my first RDD. So I'm trying to associate here on this line, I'm trying to associate a schema to my RDD. The moment I've applied a schema to my RDD, I can now convert that RDD into a data frame. So this one function will convert the RDD into a data frame. And the moment it is converted into a data frame, now I have columns with structures. Now each column has a name, a data type, a name, and data. Very similar to our relational table data types or schemas. So once it is converted into a data frame, I can run simple queries. Like here in this case, if I see on my file.rdd, I'm running a query called select ID, which is distinct, and I want to see a count. It's like select ID from a table called my file, where all the IDs are distinct. I'm saying select distinct IDs from the table and give me a count of it. Select count of distinct ID from my file. So it's as simple as that. The moment you associate a schema to your RDD, you can actually transform that into a data frame, and you can run your SQL-like queries. So that's the Spark SQL you've got. Let's see what we have done. Yeah, that's just a quick recap of Spark libraries that I spoke earlier. The machine learning libraries, it has got a very rich support for all, like I said, your decision trees, or you have, your regression models. You have different statistical algorithms that it has got. All can be supported. And GraphX is, again, I want to reiterate, it's a very popular API which does the analysis on your graph data, Twitter, social network feed, page rank we spoke about. Now, let's actually run through some quick examples. I'll see what I can show you today, so that we'll see some RDDs that we have constructed. Okay, this is a VM that I'm running today. Now what we'll do is we'll create an RDD called my file from this input file. On this RDD, I'll try to show you some values. So once I have an RDD created, I will try to run a flat map transformation so that I can split these lines. And then once I split this line, I want to see occurrence of each word. So this will, I'm saying on each word, I'm trying to create a map saying that this word, comma, how many times it is occurring on that line, on that particular line. So once I have that line available to me, I will run my final RDD to reduce it. This is just like, reduce everything on everything. So I'm reducing it by key. So let's quickly see what the content of file looks like for you. So let me show you the file content. Okay, so this is the file which contains some words on Spark, memory, Spark, and if you see each line is separated by a white space, each word is separated by a white space, and it contains around 5 lines. So now let's try to run some transformations, and then let's see some actions. And I'll also show you a DAG which is running on it. I mean, we can show you some DAG on it. So once you invoke your Spark shell, so there is a Scala prompt. As I said, the basic Spark shell is written in the entire Spark. So majority of Spark is written in Scala. So I'll try to use some Scala commands here, whatever you have seen in my example there. So first thing you should notice is the Spark context is available to you as SC object, and the SQL context is available as an object called SQL context. So these you can use. These are the readily available variables to you, so you can use them. Now let's try to first create the first RDD. It's called my file. So if you can see, I'm using the Spark context object available. I'm trying to load a text file from a directory called home Spark webinar input file. So this file, I'm loading it into an RDD called my file. There are other ways to. There are some other ways as well. I mean, you can also create some. If you're for your academic purpose, or if you're trying to learn the Spark in the beginning, you can also say you can create an object, my file, and you can assign some string, and you can parallelize it so that it just simulates a parallelism to it. Now, if you see, I've created a RDD called my file, and this RDD is of type string, and it is loading it from here. Now this RDD, the moment I've created here, there's nothing been done. I mean, it has just created an RDD called my file, and it created a pointer to it. Now if I want to see, if I really want to execute this RDD, I'll run a transformation called my file.collect. So I'm trying to apply a transformation called collect on the RDD my file, and that's where it actually executes this RDD. So if you can see, it has given me back an array of strings, and it just has returned me because I have not done any transformations on it. I just actually displayed what this RDD really contains. So it contains an array of strings. So each line is one string. I mean, if you can see from the previous example, I mean, I've shown you. So each line is a string, and it is just stored into an array of strings. Now let's run the another RDD where we will apply some transformation, where we are trying to apply the transformation called flat map. Now what we are trying to do is, on the first RDD called my file, I'm applying a transformation where each line is actually split based on the spaces. As you know that we have created some white spaces inside each line. So I'm trying to run this transformation on it. So at this point, there is a lineage created between two files, beg your pardon, two RDDs. First RDD is my file, the second RDD is map my file. So the parent RDD for map my file is my file. Now, if you want to see the DAG for it, you can see a DAG this way. I mean, let's say I want to see a DAG on map my file. So I can say map my file. I can show a previously executed DAG. Just a moment, because it takes a time to. Okay, let's actually run a few more. So to make this DAG a little more interesting, let's run a few more transformations. Now on the second RDD called map my file, I'm running one more transformation called map, which will take each word and it creates a word count for that file. So at this point, if we want to execute this and see the contents, or if you want to execute this RDD, let's see how the output looks like. So I'm now trying to run an action called collect again. So if you see from our previous example, now this each array is now, each line in this array is broken based on your, the second RDD, which is actually splitting based on your white spaces, and these white spaces split RDDs. On that, I'm trying to do a count of words. So let's say on the first line I have Spark has count 1, because I'm saying whichever word you see, you assign a 1 count to it, and it sees that there is a second word called runs, and like this word, and this has a count 1, and so on and so forth. I mean, each line, it just has broken and it just stores them as word comma 1 function. I mean, that's what I specified it to run. This is my business logic, by the way. This is my function which I'm trying to apply on that RDD. Fine, now we have a parent RDD which is pointing to the base file called my file, and then we have map my file, which is actually splitting each line based on a space character, and then I'm trying to create a word count on it. Now finally, let's do a actual reduce on it. So I'm going to do a reduce by key. If you notice, map my file, flat map, and the text file I loaded. I mean, flat map and map are the transformations on the text file that I've loaded, and these are the transformations which will be executed on single partition. So that means a narrow transformation, because I'm not doing anything for which I need a data set from a different partition. But now in this case, where I'm doing a reduce by key, so I want to get keys like Spark, maybe memory, machine, or streaming, more, and whatever. I mean, I need all these keys to be grouped together and aggregated. So I'm doing reduce by key. Now let's see how does my final RDD look like. So in this stage, I had Spark. Now if you see, the Spark count is increased to 5 because it has found 5 Spark instances, 1, 2, 3, and there are a few more here, 4 and 5. So what it does is now this is where it actually needs, it will do a wide transformation. It will collect, assuming let's say this line is in let's say these lines are in my first partition and these lines are in my second partition. So it will try to do some shuffle and sort, and like they are the boundary conditions where it will try to get the data from all nodes and then do some aggregations and show up you the results. So what advantage now we have seen is, first, I mean, this is just a very simple data set. Now assume I have some few millions of lines on which I'm trying to do a reduce by key. The first few transformations that I've applied and on which I need an action that I perform will be faster enough. But the reduce by key may take a little more time because it requires a network transfer between different partitions or different nodes. Okay, now let's see how does my DAG look like at this stage. So, I mean, the reason I've not done the debug string earlier was because I only had one transformation, so it doesn't look very comprehensive. No? But now I've applied 3 transformations and a few actions on it. Now, this is the DAG that the Apache Spark has created for my RDDs. First line, it says that I have created a Hadoop RDD. I'm reading a text file. First 2 lines, by the way. Then I've applied a flat map on my RDD, and it's called my second RDD. On my third RDD, I'm applying a map. On my final RDD, see if you see here, it's saying these are all called your map addition RDDs, your flat maps. Sorry, these are all map addition RDDs. But in this case, as I said, this is a shuffle RDD because this is a wider transformation I've applied, and I'm trying to do a shuffle and sort and do the data transfer between different nodes. So the final one is actually the shuffle RDD because you applied a reduce by key. So if you see, this is how a lineage has been built. So on different RDDs, you have built a lineage of the linkage or lineage, whichever way you want to say, and then you also know which kind of transformation you're applying or what is your action. So all these are all map partition RDDs, but this one is a shuffled RDD. So because you are telling upfront to the framework that I'm going to do a reduce by key. So when you do a reduce by key, obviously it needs a shuffle and sort. It needs a data transfer across different nodes. So this is the plan actually. This is the DAG or an execution plan which Spark creates internally, and it actually submits to the worker nodes to the scheduler, to the DAG scheduler, and it notes actually. So whenever I do an action on these RDDs, I know what transformations needs to be executed and what are the wider transformations I may have to use, or what will be my narrow transformations. All that optimizations it generally calculates. Because upfront, you know your execution plan. I mean, you're telling the framework what is your execution plan. So that's about the DAG. We have seen some of the RDDs that we created. We created some transformations. We created some actions. So that's something I had about in the lab. So I think that's all I have for now. I think if you have any questions and answers, you can go ahead and post it on your chat window. I'll be glad to help to answer some of them. And in case if you want to reach us, these are our coordinates. These are the numbers which you can reach, and you can write an email as well on these on email ID which is flashing on your screen. So if you have any questions, go ahead and ask me. I'll be able to help you. I'll be able to answer some of them. If anyone has any questions, go ahead and ask me. I can answer, and you can always reach us on these email IDs and numbers.